Hi everyone, welcome back. In this session, we are going to study the first artificial neuron, namely McCulloch-Pitts neuron, or MP neuron. By the end of this video, you will be able to learn the similarity between biological and artificial neuron, and the difference between biological and artificial neural network. For MP neuron, we will learn its computational model, excitatory and inhibitory inputs, Rojas diagram, and its vector representation. Moreover, I will also show an application of MP neuron for binary decision making. MP neuron is the first, simplest mathematical model of a biological neuron. It was invented by two scientists, Warren McCulloch and Walter Pitts, in 1943, which was inspired by neurobiology. Warren McCulloch was a prestigious neurophysiologist from the University of Illinois. Walter Pitts was a young mathematician from the University of Chicago. They collaboratively published a paper on logical calculus and created an MP neuron to mimic logic gate such as AND, OR, or NOT. In MP neuron, the two letters M and P were taken from the first letter of their name respectively. Since the initial proposal of the MP neuron aimed at handling logic gates, which are 0-1 values, the input and output of the MP neuron are all binary, based on a user-controlled threshold value, theta. We will introduce these shortly. Therefore, an MP neuron is also known as a linear threshold gate model. The signal processing mechanism of the MP neuron is inspired by the logical neuron. So let's first revisit how biological neurons are processing the signals. The main steps are as follows. Firstly, signals from neurons are received by the dendrites. Then, the soma aggregates the incoming signals. When sufficient input is received, that is, the aggregated signals exceed a certain threshold, then the neuron will generate an action potential and will fire. Next, the action potential is transmitted along the axon and output to other neurons or to structures outside the nervous systems, such as muscles. The inspiration of the MP neuron comes from the above biological process. It mimics the biological neuron to transmit signals. Let me show you a step-by-step comparison. Initially, in a biological neuron, the signals X1, X2, and X3 are received by the dendrites. In an artificial neuron, these signals are the input data. When these signals are transmitted to the soma, we draw arrows in the artificial neuron to represent signal transmission. In artificial neuron, we draw a circle to represent the soma. The circle is also called unit, cell, or node. To output the signal, we draw an arrow followed by a letter Y, meaning that Y is the output of the neuron, which corresponding to the processed signal that is transmitted along the axon to other neurons. In an artificial neuron, we often divide the node into two halves. In the left half, we write a sigma symbol to denote that the first functionality of the soma is to aggregate all the incoming signals. Mathematically, aggregating signals in a biological neuron means taking the sum of x1, x2, and x3. The result of the sum is stored in a temporary variable z. Z is called a pre-activation value. In the second half of the circle, we write a threshold value, theta, which is user-specified. This value represents the second functionality of the soma, that is, to decide whether the aggregated signals are sufficient to generate an action potential. If the sum is greater than or equal to the specified theta, meaning that the sum exceeds the threshold, then the output y is 1. In this case, the neuron gets activated. Otherwise, nothing happens. The output y is 0. From the above comparison, we can see that there are a lot of similarities between artificial and biological neurons. The input in the artificial neuron is the dendrites in the biological neuron. Their functionality is to receive signals from other neurons. The node in the artificial neuron is the soma in the biological neuron, which mainly performs two tasks. One is aggregation, corresponding to the sigma symbol, that is, adding all the incoming signals together. The other task is to check whether the aggregated value is above the threshold. If yes, generate an action potential and activate the neuron. The output in the artificial neuron is the axon terminal in the biological neuron, which transmits the action potential to other neurons or muscle cells. Moreover, there is another similarity between artificial and biological neuron, which we haven't learned in MP neuron, but will study later in perceptron lecture. That is weight. In MP neuron, due to its simplicity, each edge has no weight value. We can regard each edge to be equally important. However, in perceptron, each edge may carry different weight. The weight value on each edge actually corresponds to the synapses in biological neuron, which refers to the strength of the connection between two neurons. This table is a summary of the similarity between a single artificial and biological neuron. However, the networks of artificial and biological neurons will exhibit some different properties. Now let's look at the difference between artificial and biological neural networks. For processing speed, both artificial and biological neural nets support parallel computing, but artificial networks are significantly faster than biological ones by orders of magnitude. The speed of artificial neural nets is in nanoseconds, whereas the speed of biological ones is in milliseconds. For network size, the number of nodes in an artificial neural net ranges from hundreds to tens of thousands. The actual scale often depends on the application and the network designer. In comparison, in a biological neural net, there are hundreds of billions of neurons, significantly larger than the artificial ones. For fault tolerance, artificial neural nets have a limited fault tolerance capability. Therefore, recent years have witnessed a growing interest on the stability and resilience problem of the artificial networks. In contrast, biological neural nets are more stable. Even partial damage of the brain system will not lead to the complete failure of the biological networks. Regarding storage capacity, artificial neural nets store information in continuous memory, whereas biological networks store information in neural synapses. Now let's look at NP neuron modeling in detail. For NP neuron, all the inputs and output are binary values, meaning that x and y only accept 0 or 1 values. The node of NP neuron consists of two parts. Sigma denotes adding all the input values together. The result of the sum is stored in Z. Theta is a threshold value given by the user. Using theta, we make a decision based on whether z is above the threshold. If z is above theta, y is 1. Otherwise, y is 0. Let's take an example. Given the input data x1, x2, and x3, which is 1, 0, 1 respectively, and the threshold theta is 2, we want to predict the output y of this neuron. We first do aggregation. We add all inputs x together. The sum is 2. Then we check if 2 is above the given threshold, theta. In this example, the given theta is 2. The sum 2 is just reaching the threshold. Therefore, the output y is 1. The above example is only a very simple case, without considering the input type. In general, each input data, xi, has an input type, neither excitatory or inhibitory. Excitatory inputs contribute to the neural excitation. If the combination of excitatory inputs reaches the threshold, the neuron will fire. Inhibitory inputs impede neural excitation. It is important to note that each inhibitory input has an absolute veto power over any excitatory inputs on the decision-making. That is to say, if any of the inhibitory inputs is 1, then the output of the neuron will always be 0, and the neuron will never fire, regardless whether the sum of the other inputs is above the threshold. More precisely, let's modify the procedure for output prediction as follows. Before adding all the inputs together, we must check if any inhibitory input is 1. If yes, just output 0. Let's take an example. In this example, there are 3 inputs, x1, x2, x3, which is 0, 1, 1 respectively, and the given threshold theta is 2. Note that x1 and x3 are excitatory inputs, and x2 is inhibitory input. To predict the output y, we first check if any inhibitory input is 1. We note that x2 is inhibitory, and its value is 1. Therefore, the output y is 0. Next, I will introduce Rojas diagram. In MP neuron, since each input x has an excitatory or inhibitory type, using the traditional graph representation, we need to put a label excitatory or inhibitory beside each input, which looks a bit tedious and not aesthetic. Rojas diagrams can represent MP neurons in an elegant way. This diagram is similar to our traditional graph representation, but there are 2 differences. The first difference is the node. In Rojas diagram, the node is divided into a left white half and a right black half. The threshold theta is written on the white half of the node. In comparison, in the traditional graph representation, the left half is sigma and the right half is theta. The second difference is the edge. In Rojas diagram, for each inhibitory input, a small circle is drawn at the end of its edge. This circle can differentiate inhibitory input from excitatory input. In this example, we can see there is a tiny circle at the end of the edge linked to x2, implying that x2 is an inhibitory input. Next, I will give you an illustrative example to show the real application of an MP neuron in decision making. Tom has a plan to live in Hawaii. There are several factors that may influence his decision-making. He is considering if Hawaii has fantastic weather. Is there a diverse culture in Hawaii? Are there any gorgeous beaches in Hawaii? Is the living cost high? Does Tom have an island fever? After enumerating these 5 factors, Tom labeled them as X1 to X5. Each factor accepts a binary value, 1 for yes, 0 for no. And the output, whether to live in Hawaii, also takes a binary value. Therefore, this decision-making can be modeled using MP-neuron. Among the 5 factors, Tom noticed X4 and X5 are inhibitory inputs, which have the absolute veto power on his decision-making. For example, if Tom has an island fever, X5 equals 1, then he will never consider to live in Hawaii, regardless of how positive answers in other factors. Similarly, if the cost of living is so high, Tom will not consider his living plan as well. Because without enough money, Tom is powerless to do anything. In contrast, the first 3 factors, X1, X2, and X3, are excitatory inputs. If the combination of these input values is above Tom's satisfaction threshold, then it will promote Tom's decision-making to live in Hawaii. In this example, Tom's satisfaction threshold is 2, and here are his answers to the 5 factors. Based on this information, we can draw a Rojas diagram of the MP-neuron. Note that X4 and X5 are inhibitory inputs. Thus, we add a tiny circle at the end of each edge connecting to X4 and X5. Based on the Rojas diagram, we next predict the output of this MP-neuron. We first check whether any inhibitory input has 1 value. In this example, the value of X4 and X5 are all zeros. Then, we aggregate all the inputs. The sum Z is 2, which is equal to theta, meaning that these input factors are just reaching Tom's satisfaction threshold. Therefore, the output is 1. That is, Tom will make his decision to live in Hawaii. Next, we are going to learn vector representation of an MP-neuron. The existing formula to predict output Y can be expressed more concisely in vector forms. First, let's simplify this orange part. We first introduce a vector of 1. We use the bold font to denote a vector. Bold 1 is defined to be a row vector, and each element is 1. The length of this vector is n, which is equal to the number of inputs. We also use bold X to denote an input vector. This is a column vector, whose element is the input data, x1, x2, and xn. When multiplying these 2 vectors together, we get the following. Note that this is a dot product. The result is 1 times x1 plus 1 times x2 plus 1 times xn, whose result is x1 plus x2 plus xn, which is z. This implies that vector 1 times vector x is z. Using this relation, we can simplify the expression in the orange part. Next, we are going to simplify this part. It can be expressed concisely using a Heaviside function. In math, the Heaviside function jumping at the point theta is denoted as h theta of z, which is defined as follows. If z is larger than or equal to theta, the function returns 1, otherwise 0. This is a step function whose jumping point is at theta. It can be depicted in the following graph. We can see only when z is larger than or equal to theta, the function is on, otherwise return 0. Using this function, we can rewrite this part as follows. Note that since the shape of this function is like a step, in some textbooks, the right half of the node theta is often replaced by the shape of this step function, indicating the activation function is a step function. Finally, we combine these two parts. We plug the first equation into the second one, which produces a very concise expression for the output y. This is the vector form for predicting the output of an NP neuron. Before ending this session, let's do an exercise. An NP neuron has 3 excitatory inputs, x1, x2, and x4, and 2 inhibitory inputs, x3 and x5. Given the threshold theta equals 2, depict the RoHS diagram of this neuron, and predict its output when the inputs are 1, 0, 0, 1, 1, and 1, 0, 0, 1, 0, respectively. We first depict the RoHS diagram of the neuron. There are 5 inputs, and the given threshold theta is 2. So we draw a circle and put 2 in the left half. Among these inputs, since x1, x2, and x4 are excitatory, we use 3 arrows to represent the corresponding edges. x3 and x5 are inhibitory. Thus, apart from 2 arrows, we also put a tiny circle at the end of each edge. Y is the output. Based on the RoHS diagram, we next predict its output based on this procedure. When the inputs are 1, 0, 0, 1, 1, we first check this part. Since x5 is inhibitory and its value is 1, therefore the output is 0, because inhibitory input has an absolute veto power on the final output. Next, we predict its output when the input values are 1, 0, 0, 1, 0. In this case, all the inhibitory inputs are not 1s. Then we add them up, and the sum z is 2, which is equal to theta, just reaching the threshold. Thus, the output y is 1, and the neuron will fire. That's all for today's session. Thank you for your watching. Bye.